Hey fellas, so there's a little bit of a shift in this chapter. It happens right here, starting in 3.5, 3.5, 3.6, and 3.7 all have to do with systems. So we're not talking about functions so much anymore, but we're working with systems of functions, or systems of linear equations, which is just more than one of them. Okay, so luckily for this chapter, we're just going to deal with two equations and two variables. Obviously, later on, we'll probably step up a little bit and work with 3 or 4 equations, or even more than that. So the goal here is to learn how to solve systems of linear equations in two variables. All right, so there's different types of linear systems. All right, the most common one is this one right here, consistent independent. Okay, this is the one that you're most often going to see. This is the one you're actually going to get an answer for. There's also a no solution and a all solutions case, just like there were for the absolute value equations and the inequalities. Okay, so really quickly, what this means, right, the consistent independent case just means that you've got two equations or two lines that intersect at one point. Okay, so they're obviously going to have different slopes, your lines are, and different y-intercepts. Okay, the no solution case, inconsistent, they're parallel lines, all right? Remember, parallel lines just mean they have the same slope. Okay, so these are going to have the same slope, but a different y-intercept, all right? So they're not going to be on top of each other. And finally, the infinitely many solutions, the all solutions case, are actually the exact same line, okay? So you don't really need to know anything except that those are the exact same line. Okay, so a couple methods on how to do this. The first way is to graph. Okay, so if we graph a system of equations, it works perfectly. There's no problem with it. However, it's hard to be perfectly accurate when you're doing it by hand. If you do it by calculator or by computer, right, that's pretty helpful, but otherwise this is probably the worst method to use for solving a linear system. Right, but we'll just illustrate it right here. We need to turn both of them into y equals mx plus b so we can graph them. So y equals negative 2x plus 7. And negative 2y equals negative x plus 7. And y equals 1/2 x minus 7/2. So we go up 7 to graph the first one. And down 2 over 1, down 2 over 1. Okay, and we can draw our line. Like I said, it's hard to be accurate. Hopefully you can draw straighter lines than that. To do the second one, we go down 3.5. And we go up 1 over 2, up 1 over 2. Draw that line. And the intersection there is the answer. All right, so right here it looks like it's about probably this point right here, 4, -1 is what it looks like. Okay, so you could plug that in and double check to see if the answer is correct. Right, but once again, as I said, it's hard to get the perfect answer. It might be 4.5 and -1. It's hard to get the perfect answer when you're graphing like this unless you're using straight edge or perfect lines. Okay. So the second method, a little bit better method, is substitution, one you probably heard a lot before. Alright, so the way you do this is you just solve for one variable and then plug it into the other equation to solve for the other variable. Alright, that might sound complicated, but it's not overly complicated. Basically, the time that you'll want to use substitution. Substitution is the best method when you have any coefficient of any variable that's 1. So if you look at this x right here, right, there's nothing in front of it, so it's just that coefficient's a 1. That makes this really simple. If you don't have that, so if you try to use substitution on the top equation, right, you're always going to end up with fractions all over the place, and that's just more complicated for everybody. Okay, so substitution says solve for one variable, so we're going to solve for x in the second equation by adding the y over. And then we could take that y plus 9, since it's the same thing as x, and plug it in for x in the other equation. Okay, so that becomes 2 times y plus 9 instead of x, right? Plus 3y equals 13. Alright, distribute my 2, and I can combine my like terms at the same time, and subtract my 18. So I've got 5y equals -5, y equals -1. Okay, once I get my y equals -1, I can plug it back into any of those equations to solve for x. And so I've got x equals negative 1 plus 9, x equals 8. Okay, so the answer is 8, negative 1. You can answer this way, x equals 8, y equals negative 1, or as a coordinate, because we know that all this means is a point on the line. Okay? The last possibility is called elimination. It's also called a linear combination. Basically what you're doing is you're going to scale your two equations so they look the exact same, right? Because we can multiply any equation by some number on both sides and make it equivalent to itself. And then we can add or subtract those two equations together to cancel a variable out. So right now, there's no way to cancel out the x's, no way to cancel out the y's. But what we can do is we can multiply the top equation and the bottom equation by some numbers, right, in order to get those to cancel each other out. So the easiest one is probably to turn both the x's into 6 by multiplying the top one by 2 and the bottom one by negative 3. You could multiply by 3 as well. That wouldn't be a problem, but then you'd have to subtract the equations, and I just think it's easier to add them. So you multiply those out, and remember to multiply by everything, so 6x plus 4y equals 8, and the bottom one is negative 6x plus 15y equals positive 87. Okay, then when we add these, right, the x's go away, which is great for us. We left with 19y equals 95. Divide by 19 to get y equals 5. Okay, once we get y equals 5, now we can pick any of these equations to plug y back in and solve for x. So I'm just going to use the first one, this one up here, because it's got the smallest numbers, but you could use any of them, you always get the same answer. So we have 3x plus 2 times y is 10 equals 4. 3x equals negative 6, x equals negative 2. So the answer is negative 2, 5. Or x equals negative 2, y equals 5. Either way works. Alright, just a couple more examples here. First one is 5-2 a solution to this system. All that has to happen here is you take the 5 and plug it into both the x's, take the 2, plug it into both the y's, and test to see if it works. So we've got 5 times 2 is 10. You can just do it this way. And 2 times 3 is 6. Does 6 plus 10 equal 16? Yes, it does, so it works in the first one. The second one, we've got 15 minus 14 equals negative 1. That's not true, actually. So this one does not work, so the answer is no. It does not work. Alright, let's just we've got 4 more systems we're going to go through just to see how these work, and then we'll be done. So this first one, you could use substitution or elimination. Substitution works fine because you see the y here, the coefficient is 1, but I actually think elimination makes more sense because your y's are already set up to cancel. Okay, so that makes that real simple. So we'll just add these up right away. Those go away. We're left with 5x equals 15, x equals 3. Plug that 3 back in to get 2x plus 3 equals 7, or you could do 3x minus 3 equals 8. Either way works just fine. 2x equals 4, x equals 2. Oh, that should be a y. Wait. I messed everything up. Hold on. I plugged the 3 back in for y. That's not smart. Okay. So the x is going to go to the x's. Okay. 2 times 3 plus y equals 7. That makes more sense. So 6 plus y equals 7. And 7. Y equals 1. That's a better answer. Okay. And number 3. Okay, I think that elimination probably makes more sense here again. Right? I think what I would probably do is just multiply the top by negative 5. Okay, because the bottom you could just the bottom one you could just leave. So when I multiply everything by negative 5, I've got negative 20x plus 5y. You could again multiply by 5 and then do some subtraction, but I just like to get the subtracting part out of the way so I could just add things up. It just makes it easier for me to see. Equals negative 45. Now I can forget about the top thing, right, and just work with the bottom. So I've got negative 17x, y's go away, equals negative 34, and x equals 2. Okay, now I could plug my x back in. I'm going to use the top one because it is smallest numbers. Okay, so I've got 4 times 2 is 8 minus y equals 9. Alright, and negative y equals 1, y equals negative 1. So the answer is 2, negative 1. Back up to 4. Okay, so in number 4, we see elimination probably makes most sense again because we don't have any coefficients of 1. So we multiply. Let's just multiply by negative 2, okay, to the top one, just like we did here at the bottom. And we'll get negative 4x plus 2y equals negative 14. When you do this one, you do these adding, 4x's go away and the 2y's go away, so you're left with 0 on the left side equals negative 5. Okay, once you get to that point, then you ask yourself, is that a true statement? Okay, so once all of your x's and your y's cancel out, you're just left with numbers. Okay, you know at that point that you're either going to be at no solutions or all solutions. So if this is a true statement, it's all solutions, and if it's a false statement, it's no solutions. That's obviously false, so it's no solution. And the last one is set up pretty easily for us to do substitution. Okay, so I'll plug in x minus 4 for y, and we'll get 3x minus 2 times x minus 4 equals x plus 8. Okay, so we've got 3x minus 2x plus 8 equals x plus 8, which is, so I've got x plus 8 equals x plus 8. Right? Well, now we can see that we have the same thing on both sides. So you can subtract off your x's, you're left with 8 equals 8, and this is a true statement this time. So the answer is all solutions. That's all for this section.